Network layer delivery, forwarding and routing. Delivery. The network layer supervises the handling of the packets by the underlying physical networks. We define this handling as the delivery of a packet. Topic discussed in these sections is direct versus indirect delivery. This figure that shows the representation of the direct and indirect delivery. Figure A that shows the direct delivery from host to host, and figure B that shows the indirect and direct delivery from the host to the destination. Forwarding. Forwarding means to place the packet in its route to its destination. Forwarding requires a host or a router to have a routing table. When a host has a packet to send or when a router has received a packet that to be forwarded, it looks at this table to find the route to the final destination. Topics discussed in these sections are forwarding techniques, forwarding process, routing table. Route method versus next hop method. Figure A, routing table based on a route. For destination host B, router using are R1, R2 and host B. For destination host B, the route we are using is R2 host B. For the destination host B, the route we are using is host B. And the routing tables based on the next hop. For destination host B, next hop R1, destination host B, next hop R2, destination host B. So from routing table for host A and a routing table for R1 and routing table for R2. Host specific versus next specific method. Routing table for a host S based on host specific method. Destination A, next hop is R1, destination B, next hop is R1, destination C, next hop is R1, also destination B, D, next hop is R1. Routing table for the host is based on the network specific method. Destination N2, next hop R1. Default method, destination N2 any other, next hop R1, R2. Routing table for the host A. Here host A to the from N1 to the N2. Here we are two routers are used, R1 and R2. Simplified forwarding module in classes and addresses packet that we are using forwarded into the forwarding module. It extract the destination addresses and forward that to the search table, and finally we are getting ARP, next hop address and interface number. In classes addressing, we need at least 4 columns in a routing table. Make a routing table for router R1 using the configuration in figure that shows the corresponding table. Configuring. Routing table for R1 in the figure. Mask 26, 25, 24, 22. For mask 26, network address 180.70.60.192. For mask 25, network address we are using 180.70.65.128. For mask 24, 201.4.22.0. For mask 22, 201.4.16.0. For mask 26, interface we are using is M2. For mask 25, interface we are using M0. For 24, interface M3, 22 M1, and any others are M2 interfaces we are using. If so, the following process, if a packet that arrives at R1 in figure 22.6 with the destination address 180.70.65.140, the solution that are given here is the router performs the following steps. The first mask 26 is applied to the destination address. The result is 180.70.65.128, which does not match the corresponding network address. The second mask 25 is applied to the destination address. The result is 180.70.65.128, which matches the corresponding network addresses. The next hop address and the interface number M0 are passed to ARP for further processing. Example 22.3 shows the forwarding process if a packet that arrives at R1 in figure 22.6 with the destination address 201.4.22.35. The solution that are given here is the router that performs the following steps. The first mask 26 is applied to the destination address. The result is 201.4.22.0, which does not match the corresponding network address. The second mask 25 is applied to the destination address. The result is 201.4.22.0, which does not match the corresponding network address that is represented in row 2. The third mask 24 is applied to the destination address. The result is 201.4.22.0, which matches the corresponding network address. The destination address to the packet and the interface number M3 are passed to the ARP. And next example that shows the forwarding process. If a packet that arrives at the R1 in the figure 22.6 with the destination address 18.24.32.78, this time all the masks are applied one by one to the destination address, but no matching network address is found. When it reached the end of the table, the module gives to the next hop address is 180.70.65.200 and the interface number M2 to ARP. This is probably an outgoing packet that needs to be sent via the default router to some place else in the internet. This is the address aggregation. Organization 1, 2, 3, 4 are using for the address aggregation, and this one is the longest mask matching for the organization 1 M0, organization 2 M1, organization 3 M2. The both are merged with the router R1 and that are forwarded into the organization 4. Next example, as an example of hierarchical routing, let us consider the figure 22.9. A regional ISP is granted 16,384 addresses starting from 120.14.64.0. The regional ISP has decided to divide this block into 4 sub-blocks, each with 4,096 addresses. 3 of these sub-blocks are assigned to 3 local ISPs. The second sub-block is reserved for further use. Note that the mask for each block is /20 because the original block with masks 18 is divided into 4 blocks. The first local ISP has divided its assigned sub-blocks into 8 smaller blocks and assigned each to a small ISP. Each small ISP that provides services to 128 households, each using 4 addresses. The second local ISP has divided into 4 blocks and has assigned the addresses to 4 large organizations. The third local ISP has divided its block into 16 blocks and assigned each block to a small organization. Each small organization has 256 addresses and the mask is 24. There is a sense of hierarchy in this configuration. All router in the internet that send a packet with the destination address 120.14.16.4.0 to 120.14.127.255 to the regional ISP. This is the hierarchical routing with ISPs.